Hello guys, welcome back to LeetCode. Today let's practice LeetCode number 847, shortest path, visiting all nodes. Okay, so you have an undirected connected graph of n nodes labeled from 0 to n-1. You are given an array graph where graph of I is a list of all the nodes connected with node I by an edge, and return the length of the shortest path that visited every node. You may start and stop at any node, and here is the key point. You may revisit the node multiple times, and you may reuse edges. Okay, so let's see the example 1, this one. So we can start from node 1 and then go to node 0 and then node 2 and go back to 0 again and then go to 4 or go to node 3. So here we use 4 edges, or we jump 4 times. In the example 2 here, we start from 0, go to 1 and go to 4, go to 2 and go to 3. So here the answer is also 4. So whenever I see the keywords here, this one, the shortest path, it is very intuitively that I will think about the breadth-first search, because the breadth-first search is that algorithm that we will use to traverse a node, a graph, and find the minimum distance from 2 nodes. So it just looks really like a breadth search algorithm. But here is a key difference from the breadth search in this question. Like in the breadth search, we usually just visit a node once, and then after we have already visited that node, we will not go back to revisit that node again. But here, we will revisit the node multiple times. So like in example 1, we visited node 0 first time, and then 2, and then back. So here is the second time, and then go to node 3. So if we want to use the breadth search, here we have to make some change to the traditional breadth search algorithm. So we want to revisit the node, so that we have to make the mechanism a little bit differently. So in the traditional breadth search, usually we will have a visited set, or you may call it seen set, and we will put all the nodes that are already being visited in this set, and whenever we want to visit a new node, we will check if that node is already in this set. If it is already there, then we stop visiting that new node. So, but here, since we want to revisit the node, so we have to change what we want to put in the visited set. So let's think about when we want to revisit a node, or when we want to visit a node, and when we don't want to visit the node. So use this example 1 again. So we are in node 1, and the node we already been visited is 1, right? And then we go to 0. And then in 0, actually we can choose to visit 1 or 2 or 3. But if we choose to visit the 1, then there is no, it makes no difference. The nodes we've been visited is also the 1 and 0, so we like to choose node 2 or node 3. let's say we choose node 2 and then go to node 2 here. And in the node 2, what we already been visited is 1 and 0 and 2. And we know that the node 3 is still not being visited. So in order to visit that node, or we can say we know we already visit nodes 0 and 1 and 2, and that is not a final state. So what is the final state? We want to visit all of the nodes, right? But 0, 1, 2 is not the final state. So, and there is only one node we can jump back to, because node 2 only connects to 0. So we need to go back to 0. And then from 0 we can go to 3. So from 0 here, because we can revisit the nodes, so we can still choose 1 or 2 or 3. But if we choose 1 or 2, and this has no difference because we already visit 1, 0 and 2. If we choose 1 and 2, that is like make no difference to or contribution to our purpose is that visits every node. So you can choose visit node 3. So here we can see that when we like to choose whether to choose visit a node or not, we will consider all the nodes we are or currently all the nodes we have been visited before. So here in the visited set, instead of the current node only, I will also put another stat or another variable. Let's call it visited. All visited nodes. So this pair of values, these two values will influence whether I want to visit a new node or not. Okay, so let's use the example 1 again. So let's say we start from 1. So the current node is 1, and all the visiting node is a 1. Then we go to 0, because there is just one only just connects to 0, so there is no other nodes. So we will while we are in 0, we will have a current node 0, and here we have 0 and 1. And when we are here, we can choose 1 or 2 or 3, right? So let's just put them all. If we go to 1, then we'll have a 1 here. And then what is all the visiting nodes? It is still 0, 1. So you see that it's different from the first row. Although it is all the same node, but the all visiting nodes is different. So here is a 1. This one is 0, 1. So that means actually these two are different stats. So we can go back to visit 1 again because it's a different state. Okay, so here is a 1, and then we can also visit 2, right? So if we go there, we have a 2, and then we'll have 0, 1, 2. Okay, before I forget, let's say here is the first step, right? Or here is the 0 step. It means in here we haven't used any edges. And then when we go to 1, there is the first steps. I will use one edge. And then from here to others, this is the second steps. So in the second steps, I will go from 0 and then go to 1 or 2 or 3. So here I can go to 3 also. So if I go to 3, then I will add 0, 1, and 3. It's come from this one because we jump from this one. We jump from this node. So here we already visit 1 and 0. And then if we go to 3, so we add 3 to the all visited nodes. So here we have 0, 1, 3. Then we will go to the third steps. So in the third steps, let's see. So let's start with this one. So for this one, okay, we can only go to 0. So let's put 0 here. So we'll have a 0, and all visited nodes is 0 and 1, right? From this node 0 and 1, and then go to 0. So still here is 0 and 1 because we don't visit any new nodes. But here you can see 0 and 0, 1 is already in the set, right? He is already here, and here we have a smaller steps 1. So that means we will go to a previous stat. So it means that we will not visit the 0 again. Right, we will just stop here. So I will remove it from also, or actually we just don't put it in our set and put it in our queue. So but I will just keep it here to let you see that we have a same sets or same stats, but we will not visit that node because these two are the same stats. Okay, and beside this one, so here we just stop here because 1 only connects to 0. So let's go to 2. So for the 2, this row, then for 2, okay, so we can only go back to 0. So let's say we'll go back to 0, and here is already been visited 0, 1, 2. So here we'll have 0, 1, 2, and let's check. There is no other same stats in the visited set, right? Here is 0, 0, 1, 2, and this one is 0 and 0, 1. So these two rows are different. So that means yes, we can go back to 0 again. Okay. And beside this one, and here is another, the next element in the second step is 3. So when we are in 3, we can go back to 0. So let's say we can go to 0 in the stats, or the older visited nodes is still 0, 1, 3. And let's check if this row is already in the sets. No, it is not. Okay, so we can keep it here. Okay, so here is the third steps, and from the third steps we'll go to the fourth steps. So let's see. We will start from 0 and the 0. Okay, so again we can go to 1. So here if we go to 1, we'll have 0. We'll have a 0 and then go to 1. So here we have a 1, and then here is a also still 0, 1 and 2. And this one, this pair of values doesn't exist in the set. Okay, so we will leave it here. And from 0, 0, we can also visit 2 and 3. So let's see, put it here. We can put 2, and it's 0, 1, 2, and so it is still 0, 1, 2. Okay, so this one is the same as this one, 2 and 0, 1, 2. So actually we will not visit that node. And let's check. So you can visit 2, and then next you can visit 3. Okay, from this row. From this row, you can visit 3. So when it visits 3, then we will have a 3, and then the new stat is 0, 1, 2, 3. And yeah, we find out that this one it is the final stat. It means we visit all of the nodes in 4 steps. So that is the answer. So that is the overall algorithm. So, but I want to say that again. So here you can see we remove this one because they are the duplicate. So what does it mean? First time, let's say we start from 1 and then go to 0 and then go to 2. Right, and then go to 1, and then go back to 0 again. So when the first time we are at 0, the stat is just 1, right? But and the second time when we want to go to 0 again, the stat will be 0, 1, 2. So these two are different. As soon as they are different, it means we can go back to this one. But can we go to the third times? Let's think about if we go to a third time, like go to this one and then go back to this one again. This will like to produce a loop. So we just jump from 0 and 2 and 0 and 2 multiple times, and like infinity in infinity, and we will not jump out or stop the program. So that is not valid a process. So we want to stop that. In order to stop that, we have to have a mechanism to detect this kind of behavior. So this behavior is that whenever we are in revisit a node, and when we revisit the node, it will produce pre-existing stats that is already in our visited set. So that means if we go there, and then it will produce a loop. So in order to stop or prevent the loop, we will not go there. So here is what we use the visited set. Still other thing is like here. So we have to find a way to express the stat. So here I put here is more like a string, right? Here is a string 1 and string 0, 1 and 0, 1, 2. But create a string is not efficient. So we still have to think other ways to produce these stats. Okay, so or we can also use an array, right? So like use an array with 4 with length of 4, and then beginning we set all of the numbers here in all of them as a 0, and whenever 1 is visited we mark it as a 1. Like this one, it means the 0 node is visited. And if I have an array like this one, 0 1 0 1 0 1, then it means the node 0 and node 2 are being visited. But the array is mutable, and we cannot put the mutable array in set, because all the things that in a hash set has to be immutable, so that we still cannot use the array. So what we will use here is a number or bit. So let's think about this as a 4-digit or 4-bit number. So in the first bit or in the 0th digit bit, it means the 0 node. If that bit is a 1, like this is a binary representation, if this bit is 1, that means 0 node 0 is being visited. So this one is 0. Node 2 is also being visited. Okay, so I will talk more in coding part, like how we can use this, or how we transform from the nodes number to the binary representation. Okay, so now let's go to coding part. Okay, let's start coding. So first, let's have an n. That means the length of the graph. Okay. And then next, define our ending state. So the ending state is when all of the node is being visited. So we'll use like have a 1 and shift by n, and then minus. Let's say our n, the length of those is like 3. So the ending state is we'll have a 3 digits, and all of the 3 digits are 1s. So how do we reach that? So we will produce a 1 0 0 0, and then minus 1, and then we will get 1 1 1. So this one is like a 1 shift by 3 times, shift 1 and then shift 1 and then shift once. So here is what I did. So we'll have a 1 and then shift by n and then minus 1. Okay, so that is the final or the ending state. And then we will have a q. So the q in Python is the q. So in here I want to put 3 variables in a tuple to represent a 1 state. So the first is 0, so it is the steps. And the next is the node, so that is I. And the second is the bit represent that node I is being visited. So here I would like to have a another function. Let's call it mark bit. So I have two variables. So the first one is called stat, and the next one, let's call it in node, and then I will return an integer. Okay. So here I will have a return stat and or the one shift by node. So here what I do is like so let's say the n equals to 3. So let's say the original stat is 0, 1, 0. So that means that the node 1 is being visited, and now I want to visit node I want to visit node 2 also. So that means I want to go from 0, 1, 0 to 1, 1, 0, right? So that means I will have another 1, or okay, so I will have the original stats 0, 1, 0 and or 1, 0, 0. So that is how we get 1, 1, 1, 0. So how I reach 1, 0, 0? So that is 1 shift twice. So shift 1 will get 0, will get 1, 0, and shift 1 again will get 1, 0, 0, 0, or 1, 0, 0. So that is here. So shift the 1 shift by node times, and then or the original stat. So we'll have a new stat with the node bits being visited or being flipped to 1 from 0 to 1. Okay, so here I will call this function mark bit, and then have his original stat is 0. It means I didn't visit any node before, and then I will visit the node I this time. Okay, so this is a tuple for the I in range n. Okay, so this is a queue, and then I also have a set, visited set. Here have a list, because just like this one in the original, when before I go visit another node, I already visit this node or the original node. So here is also a tuple, and with the first one is the node I'm currently at, and the second one is the stat. Okay, so here for I in range n. So these two has to be matched. So in the beginning, we are simultaneously as the every node. So we already visit every node or every single node initially, and then we'll go from there and then go visit other node. So here is a little bit difference from what I explained in the previous videos, but I think you can figure it out. Is that here I visit all the nodes simultaneously. That means here's in the example 1, instead of just starting from 0, I'm starting from 0 and 1 and 2 and 3 simultaneously. Okay. So while Q, it means there is elements remain in the queue. So I want to pop out the element. So I will use q dot pop left. So it will pop out a tuple with 3 values in the tuple. So the first is the step, and the second is the current node, and the third is the current state. Okay, and we want to check if the current state is the ending state. If that is true, then we want to return the step. And if that is not, that means we can visit the neighbors of the current state if the neighbors is not being visited before. I mean, the combination of the neighbors and the neighbor state is not in visited set. Okay, so for n, it means neighbor. Graph of the current node. So what is the next step? State. So next state equals to we'll call the mark bit again. So with the original state, so that is the current state, and the node I want to visit, so that is the neighbor n. So if this tuple, the neighbor n, and the next state, if it is not in the visited set, so that means I can append or visit that node. So I will append that in the queue, and here I want to put the step has to be +1 because I have to use another jump, and then the next is the neighbor and the next state. And besides that, I have to also add it to our visited set. So it's the neighbor and the next state. Okay. And here we just return a number because it should always, because the graph is connected, so we will always return at line 16. Okay, so now let's run. Okay. Awesome. Okay, so here should be current state. Current state. Okay, run again. Okay, and submit. Okay, it is accepted. So here I want to analyze the time complexity and space complexity. So for the time complexity, it will produce here, like here we have a while loop, and also in the line 618 we'll have a for loop. So in the while loop, we will execute the while loop for like the elements, the length of the queue. So the length of the queue is, so the length of the queue will be determined by these two numbers, I and the stat. So for the I, we have n, that is the length of the graph, and the stat is some, we'll have 2 to the power of n. Like you can think about if we have 3 of, okay, if the n equals to 3, then the stat is for every bit there are 2 choices. So here we have 2 and multiplied by 2 and then multiplied by 2. So here we have 8 choices. So for the total stat, we'll have 2 to the power of n. And then, so here is the number of the elements in the queue. And for 9, 18, here is still for an elements in the queue will visit all of his neighbor. So in the worst case, there are maybe like n, all of the nodes in the graph is the neighbor. So the time complexity is like n squared multiplied by 2 to the power of n. So this is time complexity. And for the space complexity, so I have already an analysis that is the length of the queue. So that is n to the n multiplied by 2 to the power of n. Okay. It's a long video. If you watch till now, then I'm very appreciated. Okay, see you next time. Bye.